Welcome all to the online lecture series on Applied Electromagnetic Theory. In this video lecture, I will be dealing with the topics from first module. Myself, Rinju Mariam Raleigh, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. Here we will be focusing on the determination of inductance of a coaxial cable and two-way transmission line. And in order to understand this video lecture, we need the basics of vector calculus, the magnetic field intensity of infinite line current, magnetic field intensity of infinitely long coaxial transmission line, and magnetostatic energy density expressions. Inductance. A circuit or a closed conducting path carrying current will produce a magnetic field. The magnetic field will cause a flux. If the medium surrounding the circuit is linear, then the flux linkage is proportional to the current producing it. Mathematically, we can write flux linkage lambda is directly proportional to the current producing it, that is I. So we have lambda directly proportional to I. So changing the proportionality constant, we can write lambda is equal to L into I, where L is the constant of proportionality called inductance of the circuit. A circuit or a part of a circuit that has inductance is called an inductor. Inductance of an inductor is the ratio of magnetic flux linkage to the current producing it. So we can write L in terms of lambda and I as L equal to lambda divided by I, where I is the current through the inductor. The magnetic energy stored in an inductor is equal to half Li square, where L is the inductance and I is the current through the inductor. And energy is measured in the unit joules. Inductance of coaxial cable. Our aim is to determine the inductance of a coaxial cable as shown in the figure. So a coaxial cable, it has an inner conductor and it has an outer conductor. The radius of inner conductor is A and radius of outer conductor is B. So just before we learned energy saved in an inductor, W is equal to half Li square. Then magnetostatic energy density, that is small letter Wm, that's also is equal to half mu h square, that's same as half vector B dot h, it's also same as B square by 2 mu. So the inductance of a coaxial cable, the total inductance, that is the summation of inductance because of the inner conductor and the inductance between the inner conductor and external conductor. So the total inductance of a coaxial cable, that is the internal inductance that is due to the inner conductor and the external inductance that is between the inner conductor and external conductor. So here we will be doing it as two parts. So this figure, here in this figure we have focusing on the inductance because of the internal conductor, that is the region between 0 and A. So here we have the region, here we have considered as rho between 0 and A. And from the basics of the equation of energy, we know L is equal to 2 by I square Wm, where Wm represents the energy stored in an inductor. And just now we understood the total inductance of a coaxial cable is equal to internal inductance plus external inductance. That is L in plus L external. So the inductance in terms of magnetostatic energy density is same as 2 by I square integral over volume Wm dV. So first let's move on to determining the internal inductance due to the inner conductor. So from this expression, we know L in is equal to 2 by I square integral Wm dV. So Wm represents magnetostatic energy density, that is same as B square by 2 mu. So we have B square by 2 mu dV. So this is equal to 1 by I square mu. It's dV, volume integral. So we have the integral varying for rho, phi and z. So rho varying from 0 to L, phi from 0 to 2 pi and z varying from 0 to a. B square. So here we need the basics from the previous topic that we learned. So when we learn Ampere's circular law, we use Ampere's circular law in order to determine the magnetic field intensity of coaxial transmission lines. So from there we understood H, magnetic field intensity H, for our region of interest, that is from 0 to A, that is this region. So the magnetic field intensity H is equal to I into rho by 2 pi A square. And we know B is equal to mu into H. So here we can substitute B is same as mu into I rho divided by 2 pi A square. So that is mu into I rho divided by 2 pi A square, the all square. So here it becomes as mu square I square rho square divided by 4 pi square A raised to 4. And dV, that is rho d rho d phi dz. So simplifying this particular equation, we get it like internal inductance L in is equal to mu by 4 pi square A raised to 4 into A raised to 4 by 4 into 2 pi L. So simplifying this, we'll get it like mu L divided by 8 pi. So the expression mu L divided by 8 pi, it represents the internal inductance of a coaxial cable. So our next step, it is to determine the external inductance, that is due to the inner conductor and outer conductor. So next we have to do that. The external inductance is between the inner conductor and outer conductor. So let's consider this figure. So now our region of interest is between A and B. So this is our region of interest. So our rho varies from A to B. The value of rho varies from A to B. So just as we did before, we know the expression for L. So here Lx, that represents external inductance, that is equal to 2 by mu square B square by 2 mu dV. So here we have to substitute for expression of B. And we know B is equal to mu H. So what is the magnetic field intensity value H if rho is between A and B? That is H is equal to I by 2 pi rho. So this expression we have already learned before. So let's substitute that. B is equal to mu H. So that is equal to mu into I by 2 pi rho. So B square will become as mu square I square divided by 4 pi square rho square. And it is dV, volume integral. So we have the value of rho varying from A to B, the value of phi varying from 0 to 2 pi, and the value of z varying from 0 to L. That's the length of our conductor. So let's simplify this particular equation. Let's evaluate the integrals. We will get it like L external is equal to mu by 4 pi square ln B by A into 2 pi L. So simplifying this will become as mu L by 2 pi ln B by A, where B is the radius of the outer conductor, A is the radius of inner conductor, and mu is the permeability, and L is the length of our conductor. So now we have determined the internal inductance and external inductance. So the total inductance of the coaxial cable is equal to L in plus L external. So internal inductance is equal to mu L by 4 pi plus mu L by 2 pi ln B by A. So that you will get it like mu L by 2 pi into 1 by 4 plus ln B by A. So using this expression, we can determine the inductance of coaxial cable, and we have come to this expression by evaluating the internal inductance and external inductance separately. So next we will focus on determining the inductance of two-way transmission line. Inductance of two-way transmission line. So consider a two-way transmission wire. We have two wires with radius A. Two-way represents the diameter, and wires are separated by a distance D. So as we did before, here also we have to determine the inductance of two-way transmission line. So here also first we have to determine the internal inductance, then the external inductance. Because of the wire 1, the current inductance produced because of current flowing through wire 1, and then we have to determine the inductance because of wire 2, because a current is flowing through wire 2 also. So we know the basic expression inductance L is equal to, in terms of magnetic energy, is equal to 2 by I square Wm. In terms of magnetostatic energy density, that is equal to 2 by I square volume integral Wm dV. So just as we did before, we know the internal inductance of these conductors is equal to mu L by 8 pi. This we did before. Just now we have derived it. Now, what is the external inductance? So in the region from A to D minus A. Region from A to D minus A. So let's find it. L external is equal to, from this expression I know it is 2 by I square integral B square by 2 mu dV. So what is B here? For that we need the basics from the infinite line. So there we have H is equal to I by 2 pi rho, and we know B is equal to mu H. So B in this case, in order to determine the external inductance, is equal to, B is equal to mu I by 2 pi rho. So let's substitute here. So B square will become as mu square I square 4 pi square rho square, and dV is equal to rho d rho d phi dz. So this expression, see, this we have already learned when you studied Ampere's law, the application of Ampere's law under infinite line current. So that expression we have substituted here. Here rho varies from A to D minus A, phi varies from 0 to 2 pi, and z varies from 0 to L. So let's evaluate the integral. So evaluating the integral, you will get it like L external is equal to mu by 4 pi square ln D minus A by A 2 pi L. Just simplifying it, you will get the answer as mu L by 2 pi ln D minus A by A. So right now we have determined internal inductance and external inductance. That's because of one wire. The same will be because of the second wire also. So we can write, since two wires are symmetrical, the total inductance L is equal to 2 times L in plus L external, and that's is equal to mu L by pi into 1 by 4 plus ln D minus A by A. So this is the expression of the inductance for a two-wire transmission line. So in this video lecture we learned inductance and how to determine the inductance of coaxial cable and two-way transmission line. So I have referred the textbook Elements of Electromagnetics authored by Matthew N. Sadiko. Thank you.